All right, next we're going to look at the RL circuit. This is a resistor and an inductor. So I have resistor, inductor, and my voltage source and a switch. And when I close the switch, I have a complete circuit. However, the current doesn't appear instantaneously. As the current builds up, we get an induced EMF across the inductor, which opposes that increase. And so it takes time for the current to build up to its final value. And that's given by this equation, I equals I max times the quantity 1 minus e to the minus t over tau, where tau is called the inductive time constant, and it's equal to L over R, the inductance over the resistance. Our final value of the current will just be V over R, the resistance of the circuit, since after a long time, the inductor just acts like an ordinary wire. And so in terms of the voltage, I have V equals V max times the quantity 1 minus e to the minus t over tau. Notice this is very similar to what we got for the charging of the capacitor. So the equation is very much the same. So the activity we're going to do, a similar activity as in the capacitor, we're going to measure the time to reach the half maximum. So here we have T1 half is the time to reach half the maximum voltage. So we have 1 half V equals V times the quantity 1 minus e to the minus t1 half over tau, or e to the minus t1 half over tau equals 1 half. And then 2 equals e to the t1 half over tau, since the minus is just the reciprocal. Then I can get at the exponent by taking the log. So I have log 2 equals t1 half over tau, or tau log 2 equals t1 half. Substituting L over R for tau and solving for L, we get L equals R times T1 half divided by log 2. So this gives us a way to measure the inductance. So we'll find the time to reach half the maximum voltage, and then we can get a measured value for the inductance and compare that to the actual inductance of the circuit using an inductance meter. So that's the activity we're going to do this time. So I'll set up the circuit for this one and then get back to the video on that. Okay, here's the electronics kit with now arranged with the inductance. Our coil is this device right here, and I put in an iron core to increase the inductance. Here's our input. I have a wire connection to the coil, and then another wire connection from the coil to here, and then I have my 10 ohm resistor from here to here, which goes back to the supply. So there's my simple series circuit, and then we're going to input a voltage. And so here I have measuring, whoops, I got this in the wrong spot. I want to measure the voltage across the resistor, so that's going to go between here and here, and now I can measure the voltage across the resistor. But first of all, in my simple series circuit, this is not the only resistance. The coil will actually have some resistance as well. So I want to measure the complete resistance of my circuit. So I'm going to disconnect this one, and I have a multimeter over here. So I'm going to remove these inputs for my power and replace this with my voltmeter. I have my voltmeter set for ohms. I don't know if you can see this, but we actually get 15.6 ohms. So I'm going to record the true resistance of the circuit is 15.6 ohms. Now, I have already used an inductance meter to measure the inductance of our coil, and that inductance came out to be 33.8 millihenries. So I will give you that data as well, so don't worry about that one. Okay, so 33.8 millihenries is the inductance of our coil, and 15.6 ohms is the resistance for our circuit. So I reconnect my power supply, reconnect my voltage sensor across my resistor, and now the circuit is all set up, and so we're ready to collect the data. So I'll pause and move the camera over to the computer so we can see that. Okay, I have the activity loaded up. Here's the Capstone software, the LR circuit activity. This is the workbook, gives a description of the activity. Page 2 tells me what all the settings are. I'm going to collect data for 0.12 seconds. I'm going to input a positive square wave with an amplitude of 5 volts, frequency of 30 hertz, and then my sample rate is 10 kilohertz. So I check my hardware setup, that's okay. I check my signal generator, set to auto, 30 hertz, positive square wave, 5 volt amplitude. So I can close that. Now on page 3, I have a graph where my data is going to display. So I have the circuit all set up, the software set up. I can click on record. And here's my data. So you can see how I get a rise in the voltage across my resistor. And we want to do like we did with the capacitor lab. We want to measure the time it takes to reach the half the maximum. So I click up here to get a coordinate tool. My coordinate tool, then I can put it onto my graph, and I'll check my maximum voltage. My maximum voltage is 3.119 volts, so I'm going to go down to about 1.5 to 1.6 is half the maximum. So I can use the arrow keys to control this. I go down to the find the half maximum. So here's 1.6, and I get, for my time, I get 0.0347 seconds. And then I go down to the bottom to get the lowest, and I get 0.0332 seconds. Okay, so 0.0332 is at the bottom, and 0.0347 is at the top. Okay, so let's do another run just to make sure. So I do another run, and I go to run number 2, add a coordinate tool. Again, put it on my graph, so find the 1.6. 1.5 to 1.6. And again, I've got 0.0347, just like I did before. Go down to the bottom. 0.0332, exactly the same again. So I now have the time at half max and the time at the bottom. And so the difference of those two times will give me the time to reach 1/2 max. Then I can go ahead and do this calculation and get a measured value for the inductance and compare that to the given value. So now we have all the data for this run, and we're finished with this activity for as far as the data collection. So you will then have to do the calculations and answer the questions and then turn in the lab report. So that's the end of this activity. So this one's actually pretty short, collecting the data, but you can see it makes really nice graph here. All right, so we only have one more lab after this, and this will be the LRC circuit, which we'll see behaves quite a bit differently.